Hey everyone, what we're going to go over today is a system that allows you to make your footsteps for your player characters or your NPCs change based on the material of the surface they're standing on. This is similar to systems you might have seen in games like Thief or Dishonored, or to be honest, a lot of modern games these days. I'll say up front that this isn't a perfect system, but I do think it's good enough, at least for the purposes of the game I'm making, and probably a lot of other people's games as well. Now, while it's quite easy to get a material from an object, it's a bit harder to get a material relative to where the player is standing on that object, and that's the actual special part about this video to me that I haven't seen covered anywhere else. So if that's interesting, then hey, I hope you keep watching. Okay, so we start with this node, which is just Raycast. That points down a decent amount. It's just set to my environment layer, and it collides with bodies. Now, if you take a look at its script, there's a bit of stuff here, but it's actually less complicated than it looks, so just bear with me. This is for storing our current colliding surface, so the mesh instance we're currently colliding with. This is our surface sound type, which is what we export at the end of this to let other systems know what kind of material we're standing on. So whether it's rocks, sand, grass, wood, whatever. This is a geometry node. You don't need to understand this too much. We're only going to use one function out of it. And this is just our body, our parent in this case, which would be the player for this node. But for NPCs, this would be their body. And next we have an array, which we're going to use in a moment. And then all of this is run in the physics process. So first we check if we're colliding and if our body is moving. Then we store the colliding object that our raycast is colliding with in a variable. After that, we check if this colliding object that we're now colliding with is different than the one we have stored that we were colliding with before. This basically means that every time we move on to a new object, we do certain logic again. After that, we check if the parent of this colliding object is a mesh instance. You don't necessarily have to do this, as if we look here, this is just a model that I exported from Blender, very simple. This static body, this is the object you'll collide with, and its parent will always be whatever your mesh instance is. Whatever your actual graphical mesh is when you export from Blender. So if this is what you know the arrangement is always going to be, you don't actually need this part here. I just have it because I'm developing this and I don't want it crashing for no reason. After that, we set our colliding object as our current colliding surface, and then we check if our surface count is equal to 1. And this is actually as much as you need here, or actually just these two bits here. If your mesh only has one surface. So if all you want to do for your game is detect if the meshes on the floor, which only have one surface, are a given material, you only need this, because you can just get active material 0, which will always be the only material you have on it, and that's fine. Like, the rest of this is only if you're doing the complex task of resolving a mesh that has more than one material. So after that, if this is false, we're going to build some mesh data tools. And if you don't know what a mesh data tool is, again, that's fine. I'll explain it right now. So if we come down here and we actually look at mesh data tool, pretty much all it is just, it's a thing that helps you do certain math tasks when it comes to meshes, and you can do it with meshes that don't actually exist because they only become real when you commit to surface here. So what we do is we first clear our MDT array, because this only gets called when we're walking onto a new object, so we want to clear our previous mesh data tools. Then what we do is we get the mesh of our current colliding surface, and then using that we run into a for loop here, which for every surface on that mesh we create a mesh data tool from it using create from surface here. That function just requires our mesh, which we defined here, and the given surface index, which we get from getSurfaceCount here. And we append that to our array, and then here we call this function if our array is bigger than 0, basically, because this for loop will only run if it has any elements in this array. So the first thing we do is we pass in our collision point, which we're going to use later. And then we run this logic for every mesh data tool in our array. Now, I'll explain this little bit in a moment, once I get down to the bottom. So every vertex in our mesh data tool, because what this does here is it creates a virtual mesh based on the material we've given it. And that's populated with normals and UVs and vertexes and so on. So for every vertex in that virtual mesh, we want to get the faces of that vertex. So every face that vertex is involved in. And if we briefly look at Blender here, this is what these faces will look like in Godot. They're triangles, they're not squares or anything like that. So you can imagine for every vertex, so if I go into vertex select here, so this vertex is involved in making this mesh and this mesh, but this vertex is only involved in making this mesh. So back into Godot. Yeah, so once we've got our faces, we want to get their normal and then run a dot product to make sure they're actually pointing in the right direction, because we don't want faces that are looking, down, right? Unless your game involves walking on the ceiling, in which case you might want to actually avoid this line. So once we've done that, we're going to assemble our triangle, and in order to do that, I'm briefly going to explain this node here, this function here. So if we search get face vertex, returns the specified vertex of the given face. So you pass it a vertex index here, and then an index based on whichever face you're working with. You see here, it must be 2 or less because it's a triangle, like I said. And a triangle can only ever have 3 vertices. So what we do is this will return an index of a given vertice. Then we use getVertex to actually get the vector3 data of that vertice. And then we do that 3 times for the 0, 1, and 2 of our triangle. Plan this out, actually. And next we have our ray intersects triangle, which is how we finally figure out where we're actually standing on the mesh. And we do this using our geometry node, which we defined earlier. And what we do is, actually, if I show you this function here, we need a from vector, which is basically our position, and then we need a direction vector, which is the point that this ray, the direction this ray is pointing in. So you can imagine this like an infinite line, right? And this is just going to point from wherever you start from to that direction forever. And using this A, B, and C here, we build a triangle to check if that's pointing through that triangle. So if we go back, that's exactly what we do. We first get our origin of our Raycast node, and then we get our direction to our collision point, which makes our direction. Then we convert each of our vertices into global coordinates, because otherwise this won't work, and we call that function on our current colliding surface. If that returns true, as in we are standing inside the triangle, then we're going to do this to figure out what kind of sound we should make. And this is just a bit here to visualize this for you. And actually, I'll run this and I'll show you. Okay, so if we move forward here, you can see that it tracks our position on the mesh perfectly. Figures out which triangle we're in, and the cubes visualize pretty well exactly where we're at. And this works both on just flat surfaces like this and more complex ones like this. Now, there is a problem here. So this mesh over here, this has been heavily subdivided. Actually, I can show you this. I get a try mesh here. Okay, yeah, so you can see this has a lot of subdivisions, right? Like probably more than you would typically, put into a game like this, but this is just for the sake of argument to demonstrate a limitation of this approach. So if I now relaunch this because it crashed and walk onto this, yeah, you'll be able to see the problem immediately. Okay, yep, we lock up, and I think I'm running at about like -5 FPS or something. Oh, yep, actually literally 1 FPS there for a moment. That's interesting. Yeah, and trust me, that's not an artifact of recording or anything like that. That's just because of the way we're trying to do this. Basically, iterating through every vertex and then every face attached to that vertex when you have a highly subdivided mesh is never going to be efficient. I have experimented with trying to find the nearest vertexes or trying to sort the vertex array to prioritize the nearest ones, or finding which vertices are contained within a cylinder, but none of those solutions really worked very well. Okay, and now before we move on, I'm going to demonstrate this optimization here. Actually, I don't really need to demonstrate it, but basically what this will do is it will make it so we don't have to check the mesh data tool that we know we're already on. Right, so what this will do is every time we run through, it'll check if we already know which one we're on, and if that's the step we're on, we just skip it, because for a given mesh, we only want to check the surfaces that we know currently don't but could contain the player, right? So yeah, let's move on. So the last step in this journey is this analyze material path function here, and all we do is we just pass in the material assigned to this mesh data tool. Since this came true, we know this is the right one. And then we return early so that we don't keep iterating through materials or surfaces that we don't need to. So if we go down to this function, we can see that all it does is it converts our resource path into a string. The thing of it, I'm not sure if that's a string by default, but I convert it anyway. And then we look for certain keywords. So here we look for grass, and if that comes true, we set our sound type to grass, and then we do the same for rocks and stone and metal and tile and fabric and however many materials you want to have in your game, or at least however many unique footstep types you want to have in your game. Then we have a getter here, so that if a given node needs to extract this kind of data, it can. But here I set this manually on my player node up here. So if we go into that node, you can see that's just a setter down here, and that sets a footstep profile variable that's declared up the top. And here, I play my footsteps with an animation player based on how my model is standing. So a given frame of my model just has... actually, I can show you this. I go down to here, go to my animation player, and I, like for example, just my walk cycle. All I do is I add a method track, which calls the play footsteps anim either false or true for left or right on my player. And then what I do is, since I have 2 sound nodes, so one for each of my feet, I just get child here, and I cast this Boolean variable into an integer, with which I use to get a specific child index. Yeah, and then I stop it if it's playing. I set its stream to a randomly selected file from a sound singleton, and then I play it. If we look at that singleton, this is very simple, but this just matches the profile that's being given. So again, grass, stone, wood, tile, whatever. And then I have preloaded dictionaries here full of sound files. At the moment, I only have some placeholder grass sounds, but you can see eventually here I'll implement all the other sounds I want to have. Well, I got nothing else to say, so I'll stop it there. But if you have any questions, then certainly feel free to ask, or if you feel I haven't explained something adequately, then I'll do my best to help you. On that note, if you have a better way of doing a system like this, then I'd certainly like to hear about it, or if you think there's a more optimal way of going about what I've done. Thanks for watching, and hopefully I'll see you next time.